Good afternoon. So for what we have seen, we have analyzed the linear phase FIR filter for the case of an symmetrical response when n is odd and when n is even. Okay. So today what we are going to see about it now, we are going to see about an analyze about an antisymmetrical response for the case of n is to be odd. Okay. So let me consider the frequency response h of e power j omega is equivalent to summation n is equal to 0 to m minus 1 h of n e power minus j omega. So we'll be making of an frequency response of impulse response, which can be written as an so h of n summation is equal to 0 to m minus 3 by 2 h of n e power minus j omega, and similarly plus summation n is equal to 0 to m minus 3 by 2 h of m minus 1 minus n e power minus j omega of m minus 1 minus n. So we know that for antisymmetric impulse response, h of n is equivalent to minus of h of m minus 1 minus n. Okay. So we'll be replacing over on it. So it will be changed as an sign, where is a positive symbol will be given as an negative symbol. So we'll take a common as an e power minus j omega m minus 1 by 2. So it will be replaced as summation n is equal to 0 to m minus 1 by 2 h of n e power minus j omega odd value, then again minus value. So we know that this factor will be equivalent to equal to that is of your 2j sign value. So taking as an j to be the outside, so we'll have of an 2 into sign of value. J will be replaced as an e power j pi by 2. So the outside of the bracket will be replaced as e power j pi by 2 minus of the value into of your 2f value. So when you are having of the, we have to find out the magnitude and the angle response of the given response. Okay. So this is the case when you are analyzing of the antisymmetric. What you should remember of it, Abdina, for symmetrical response, h of n is equivalent to h of m minus 1 minus n. Whereas in the case of an antisymmetrical response, h of n is equivalent to minus of h of m minus 1 minus n. Okay. This is the analysis what we'll be doing over on it. So similarly, we have to make of an what is n is odd and what is n is even. So when you are analyzing for n is even, so we have to split up off into the equation. So define again, we'll be taking off an antisymmetrical response. Then again, you take the common factor. Then common factor, we can able to know that there is about your summation of your value. So we'll be having of our so equation will be replacing 2j of value. J will be replaced by e power j pi by 2. So then again we'll be having of an e power j pi by 2 minus of the value. Okay. So in terms of an cosine, we'll be having of an sine value, sine omega of m minus 1 by 2 minus n. Okay. So this is the way to analyze your linear phase FAR filters. Okay. By having of an magnitude and the angle response of the given filter. Okay. The next thing we are in need to know about how to realize the FIR filter. That is in different structures. Okay. That is we have to explain the sketches, the structure of filters. Okay. Actually, the realization of FIR filters can be done by means of an transversal structure, linear phase realization, and we'll have of an polyphase realization. Okay. So let me see one by one. So when you are saying about an transversal structure, actually we'll have two different realizations. One to be the direct form, another one to be the cascade form realization. Okay. For the case for the analysis of a direct form realization, the system function of an FIR filters, which can be written as an h of z is equivalent to summation n is equal to 0 to n minus 1 h of n z power minus n. Okay. So we'll be splitting up the equation by replacing n is equal to 0 to n minus 1. So when you are replacing, what will happen? So if you are putting n is equal to 0, so n power 0 will be 1. So we'll split up this equation into h of 0 plus h of n z power minus 1 plus h of 2 z power minus 2 up to h of n minus 1 z power minus n. Okay, so let me this be equation 1. Okay, so if you are taking a result, if you are finding the realization of an y of z, so we know that y of z by x of z is equivalent to your h of z. So just will be multiplying, cross multiplying the equation. So what will happen? Y of z is equivalent to h of 0 into x of z plus h of 1 into z power minus 1 into x of z plus h of 2 into z power minus 2 x of z. So far it will be going over on h of n minus 1 z power minus n minus 1 into your x of z. So this is to be named as a direct form realization. So when we are seeing of the equation 2, So what you can able to understand Abina, so it will be requiring n multipliers. So multiplication of the factors. See over on it, h of 0, h of x of z, h of n, x of z, h of 2, x of z, h of n minus 1, x of z. So we'll be requiring of an n multipliers, and we'll be requiring of an n minus 1 addition adders. Okay. So it is to be our h of n minus. Okay. And similarly, n minus 1 delay elements. So we'll be requiring of an three different values, one to be the multipliers, and then next to be the adders, and the next to be the delay element. So we'll be requiring of an n minus n multipliers, n minus 1 adders, and n minus 1 multipliers. So this already we are seeing IAS structure. We know that, I think so. So directly we'll be multiplying h of z to be z power minus 1, z power minus 2, z power minus 3. So corresponding with the factors h of 0, h of 1, h of 2, h of n minus 2, h of n minus 1. So this is combining with the adder value, we will be obtaining to be our y of z. Okay. So this is the way to realize our direct form. The next one to be the how to realize using about a cascade realization. Even that we know that. Okay. So how we'll be doing often? So the equation h of z is equivalent to 1 plus 2 z inverse plus 6 z power minus 2 plus 4 z power minus 3 plus 5 z power minus 4 plus 8 z power minus 5. We know that h of z is equivalent to ratio of y of z by x of z. So make a multiplication over on it. Okay, so this is the direct form realization. Okay, so h of z is equivalent to y of z divided by x of z. So which is equivalent to multiply with the value of x of z. So how many delay element will be requiring? 5 delay element. So we'll have this is a 5 delay element. Okay, so we'll be having of an 5 delay element, and how many adders will be requiring? So we'll be requiring 1, 2, 3, and then 4, 5 adders. So we'll be requiring of an 5 adders. This is about your scalar multiplication value. Okay. So this is the way to realize about your cascade form realization. Sorry, direct form realization. So when you are saying about a cascade, cascade is nothing but a multiplication of the two values. Okay. h of z is equivalent to, so we'll have two factors, h1 of z and h2 of z. So let it having h1 of z is equivalent to 1 plus 2 z inverse minus z power minus 2. Similarly, h2 of z is equivalent to 1 plus z inverse minus z power minus 2. Okay, then again by having of a direct form realization, so you separate into of an y of 1 of z divided by x1 of z. Similarly, y2 of z divided by x2 of z. Okay, then combine these two realization. Okay. So next one, we will be knowing about an linear phase realization. So we can know that linear phase FAR filter is equivalent to h of n into h of n minus 1 minus n. Okay. So this is the way 1 by 2 plus 1 by 3 z power minus 1 plus z power minus 2. Okay. So when you are saying about an lattice structure, the lattice structure formulas are given as for 0, the value to be 1, for m, the value to be k power m, for k, m minus 1 into k plus m of k into m minus 1 into of your m minus 1. So let me have a k1 is equivalent to 1 by 2, k2 is equivalent to 1 by 3, k3 is equivalent to 1 by 4. So we'll be determining the FAR structure. So the coefficients are given over on it. So we can able to know that q of 0 is equivalent to 1, 3 is equivalent to, so 2 is equivalent to k2. So k3 1 by 4, 1 by 3, and 1 is equivalent to 1 by 2. So this is the value 1 by 2, 1 by 3, and 1 by 4. So this is our equation. So substitute over here for m is equivalent to 2 and k is equivalent to 1, for m is equivalent to 3 and k is equivalent to 1. Similarly, for m is equal. So different analysis we'll be doing over there. Okay. So this is the way to realize about your lattice filter coefficients. And when you are saying about so far we are seeing about how to realize our FIR filter structure. Okay. The next we are going to see about designing of an FIR filters. So when you are saying about the designing of FAR filters, so already I said you that it can be designed by using of three techniques. One to be the Fourier series method, second one to be the windowing method, and third one to be the frequency sampling method. Okay. So let me see one by one. The first one to be the windowing technique. So windowing technique, what you should do it for Dina. Actually, the desired frequency response of any digital filter will be periodic in frequency, and it can be expanded in a Fourier series. So while you are expanding in Fourier series, hd of e power j omega, which is equivalent to summation n is equal to 0 to n minus 1, hd of n e power minus j omega, where hd of n is to be the Fourier series value. It is 1 by 2 pi integral of minus pi to pi h of e power j omega into e power minus j omega into d omega. So important factor, we have to know what is Gibbs phenomenon. Okay. So Gibbs phenomenon is a repeated 2-mark question. Okay. One possible way of finding an FIR filter that approximate h of e power j omega would be truncating the infinite Fourier series n is equivalent to plus or minus m minus 1 by 2. Okay. This abrupt truncation of the series will lead to an oscillation that is in both passband and stopband. So this phenomenon is known as an Gibbs phenomenon. Okay. So when you are when you make an approximation of h of e power j omega, it would be truncate at the infinite Fourier series. Okay. So this truncation will lead to oscillations for the case of both passband and stopband. So this phenomenon is known as an Gibbs phenomenon. Okay. So already I said you that in windowing method, we'll have a three different method: rectangular window, Hamming, and Hanning windowing method. So when you are analyzing a rectangular window, it is to be easiest to win. We can use a formula of an WR of n, which is equivalent to, the value will be equivalent to 1 when the limit is varying from m minus 1 by 2 to that is minus m minus 1 by 2 to plus m minus 1 by 2. Okay. So that is to be the rectangular window. Similarly, when you are saying about an Hanning window, the Hanning window formula, which is the 0.5 plus 0.5 cos 2 pi m minus 1. Okay. For the limit which is given over there. For the Hamming window, how we can able to remember it? Instead of having 0.5 plus 0.5, we'll have about an 0.5 plus 0.46 cos 2 pi of m minus 1. Okay. So this is about the introduction of a windowing techniques. Okay. Let me see briefly on the next class. Thank you all.